Okay. So today what we're going to look into is field evaporation physics. So the last 2 times, first we had a quick introduction of how atom probe tomography works. Then we went through the instrumentation just so that we can kind of understand what we can interpret and what information we don't necessarily have. And now we're going to look into field evaporation physics, because this is essentially how everything works. Everything works. So you've got some kind of specimen with atoms at the end, and they need to come off at a very specified time and then fly somewhere. And this is the basic principle. And then the question is, of course, if they're solid materials, typically atoms don't want to come off. Otherwise, it wouldn't be a solid. Otherwise, it would be a gas already. And so the question is, how can we make them come off voluntarily or semi-voluntarily? And of course, we've discussed it a number of times already. The way we do that is that we apply a positive voltage here. So that we apply a U plus, positive voltage here, positive, and then a negative voltage, or not really a negative voltage, but a ground voltage, typically to a counter electrode. The ground counter electrode is typically connected to ground, and the question is then, what does the field do? How do things change? What kind of sort of non-ideal situations can we encounter so that we can interpret the data that we are going to get? And that means we're going to look into the general field evaporation physics. In the simplest form, that's just the image hump model, which is a very simple, just essentially thermodynamic model. But it's been relatively successful for now 80 plus years almost. But we know very well what its limitations are, and nowadays we're also starting to get into quantum mechanics. But there we haven't understood enough. There's maybe 3-4 papers where people are starting to do that, so not enough for a lecture. And this only predicts sort of singly charged ions coming off. So we're going to look into post-ionization theory for everything that has more than one charge. We observe up to 4 plus ions sometimes. The question is, why is that? Then we look into fields in insulators, because that's what interests us a lot these days. The reason why we have lasers on our atom probes is so that you can measure non-conductive materials, which can be geological materials, which can be biomineralized materials, a whole suite of different things. We're going to look into field-induced stresses, because mostly our experiments end because our specimens break. And the reason is we have field-induced stresses, and the question is, how high are they? And how do they go, for example, with the voltage that we apply, the high voltage we apply. Then we're going to look into local magnification. So all of this is up to here. This is essentially, up to here is essentially looking at single atoms, what happens to a single atom. Then this is essentially what happens to the entire tip in an ideal case. So, all atoms have the same properties across the tip, no variations. And then we're going to look into what happens if we have variations in the evaporation field. So here we've got single atom effects. Here we've got uniform tip effects. And here we have non-uniform tip effects. And they're interesting for us because usually we don't work on pure materials because they're pretty boring. Usually we have more than one phase, for example, or different atoms in there. And then all of these things come into play. Local magnification is essentially if we've got different phases in here, one might evaporate easier than the other. And then we will get some the tip maybe looking a little bit odd-shaped, not exactly round. Chromatic aberration is when we have different atoms that they might take slightly different trajectories. And preferential retention is essentially pretty straightforward. Is some atoms might stick to the surface a bit more than others. So they might come off a little bit later than what we expect them to. And this gives us aberrations in the z direction. So this is all local magnification and chromatic aberration are in x and y, and preferential retention is in z. So x and y is sort of the typical x and y, meaning laterally here. Then we're going to look into voltage pulsing. So what effects do we get from voltage pulsing and from pulse shapes? And very importantly, what effects do we get from laser pulsing? Because voltage pulsing typically doesn't change much around the field evaporation physics. The atoms may have more or less energy. This is important for us for the time resolution and for the mass resolution. But here with laser, we change the temperature, so we change quite a lot of stuff that's happening on the surface. Okay, so the basis, the image hump model. I think we already went through it once, so we can be a little bit quicker now. And essentially, the image hump model is describing a process where an atom becomes a positively charged atom and then leaves the surface. And the process by which it does is first essentially forming an ion, and that ion then wants to come off. You can think for yourself how realistic that is, that an atom just spontaneously becomes an ion on the surface. But it's a model that's been very good in predicting what the threshold fields are. So what the fields are that we need to get field evaporation. Not necessarily of the kinetics and not necessarily of the pathways that the atoms take as they leave the surface. And this is why we have only one coordinate. We have only one coordinate. So this is essentially the equilibrium x. So this is, let's call it x0 here. And then if you want to get a little bit closer, you've got repulsive forces from the other atoms, pretty straightforward. And then if you leave here, you've got attractive forces if you have an atom. And so essentially, we can just take a regular Lennard-Jones potential, and you all know from fundamental physics, and our regular Lennard-Jones potential would be this potential here. And we took as potential 0 essentially the energy of the free atom. And this is 0 in this case. Of course, it's potential, so we can put 0 wherever you want. And in this case, it's quite clear. The atom would be happily sitting here and would thermally be oscillating up to a certain energy amplitude. Lateral amplitude, spatial amplitude, which also corresponds to a energy amplitude. And of course, if we add a field, then nothing will happen because an atom isn't charged. And this is already where the first approximation comes in, because while an atom is not charged, an atom is polarizable. So it has a nucleus and it has electrons. And if you separate nucleus and electrons, then you will get a polarization. And a polarized atom doesn't necessarily see a force in an electric field, but it sees a force in a field that has a gradient. If there's a field gradient, then you will get a net force. And so let me just change pen color. And so now, what would see an influence is an ion. But if we want an ion, then we need to add additional energy. And the energy that we need to add is essentially the sum of the ionization energies. If we've got a charge of n, so we've got an n plus ion, so we need to essentially put in the sum of the ionization energies up to ionization n. In our case, it's typically just 1, at least at the surface. But we also gain some energy, and that is n time. Again, if we've got an n plus ion, 1 plus ion, just once the work function of the atom. So phi e is the work function. Because of course the electron goes back into the solid. This essentially then would mean that the potential energy curve for an ion would be up here, and there's no way that thermally we'll get there, even considering a Boltzmann distribution, just simply because we're typically at 20 Kelvin, 30 Kelvin, 40 Kelvin. So we have definitely not enough thermal energy to get there, because of course you know what evaporation temperatures for metals typically several thousand degrees, so very far away from where we are. But when we add a field, and I'll change the color once more. If we add a field, why not magenta? If we add a field, then we have an energy contribution of minus n times charge times the elementary charge of the ion. The elementary charge, n times for a one charged ion, times the field times the coordinate the atom is at, or the ion is at, away from its zero potential. This is just the energy gain with respect to any point of origin. And so if this term becomes large enough, and so here we've got a couple of electron volts energies typically, so you can imagine we need volts per nanometer kind of fields in order to be able to make a contribution to this. And if we have that, so volts per nanometer level fields, then we will get a potential energy curve that looks like this. Which is just a modification of this potential energy curve times the energy contribution from the field. And what that means is that we have got an interesting point here, which is the crossover point. And above the crossover or beyond the crossover point, is there anything left? Green is left. So beyond the crossover point, so here we've got the atom stable, and here the ion is stable, or has the lowest energy. Which gives us a sum energy curve then essentially that looks like this. And of course it means we have an energy barrier, Q, that depends on the field F, which is already written here. And the good thing is we can influence the field F. It's proportional to the external voltage we've applied. So if we change the voltage, we change the field, and so we also change the energy barrier. And we can make the energy barrier 0 as well, which is not usually what we want, because then all of the atoms want to come off at the same time. So typically what we want is we will still want to have some residual barrier. But of course it's dependent on field, and typically if we have atom probe tomography or any kind of pulsed field evaporation, then typically what we have is we've got a voltage over time that it might look something like this. with this being our pulses. So we can just make that also 0 for a very short period of time. Just that we get enough atoms, or as many atoms as we would like, and that's essentially something we set on the experiment. Okay, but what we observe is also that we get post-ionization. Post-ionization means we don't always see atoms with a 1+ charge, but rather we see them with higher charge states. So for example, if I have gallium, gallium typically I get as gallium plus. Sometimes at very low temperatures I might get gallium 2+, but typically gallium plus, because gallium, the first ionization energy is relatively low and the second one is relatively high compared to that. But tungsten or molybdenum we will see up to 4+ if the temperature is low enough. And the question is how that happens, and it doesn't necessarily happen directly at the surface, but it happens a little bit further away. And the reason for that is that if we look at the energies or the energy levels in the atom, what will need to happen for further ionization is that the electrons will need to move into the solid above the Fermi level. And the question is that an energy gain, yes or no? And if we look at the potential, so typical potential well of an atom for an electron looks something like this. If we look at potential versus distance x, and our atom this is where the nucleus is, and the potential energy typically looks something like this. And then you will have the typical energy levels. You all know that from fundamental physics, what energy levels look like in a potential well that is in this case a 1/r kind of potential well from the nucleus, which is positively charged, and the electrons negatively charged. And so what would happen is also here, if I put a large field on, is that I get a tilting. Of course, here the atom levels are just in the middle. So I get tilting, and that means that the potential energy well that the electron sees gets tipped. Because of course the electron also sees the field, and we get something that looks a little bit more, if this is where the atom sits, looks a little bit more like this. A little bit more like this. And then here we've already got the finished sketch. So this is essentially where our ion sits at this very moment in time. And here what we have is not something going towards 0, but essentially an energy barrier like I've sketched here. So we've got a little energy barrier. So this is our energy barrier. And the energy barrier is obviously finite. And even if it was infinite, electrons can still tunnel. Because the wave function goes out. And so essentially what can happen is that we get electrons tunneling, through here. And this can produce higher charge states. And you can already imagine that the probability of tunneling will very strongly depend on what that distance is. So you already had that in your basic physics courses. Essentially, the tunneling probability decreases exponentially with the distance. So this can only happen at very short distances, but not at super short distances. But because it's super short distances, the energy level that the electron comes from might be below the Fermi level. So it would need to gain energy in order to be able to go into the base solid. So this would not be a spontaneous process. Whereas if the ion moves a little bit further away, so let's just draw it a little bit further away. If the ion goes a little bit further away, then the potential energy well would look a little bit more like this. And of course, relative to the 0 point here, then we would have a zero energy level here. We also call this very often highest occupied molecular orbital. Highest occupied molecular orbital. Because it might be a molecule, typically it's just a single ion, but it might be a molecule. But here, of course, the tunneling distance then would already be quite a lot longer, but the energy incentive would be higher. And this is a trade-off. If you're too close, you cannot get ionization because the electrons would need to gain energy. And if you're too far away, the tunneling probability just becomes very low. And somewhere in between, we can have post-ionization. And so if I change the field, still the field being high enough for field evaporation, what do you think? When do I get the highest probability for post-ionization? If I have a low field or if I have a high field? Well, what would happen if I have a high field? Well, remember, this is EFX, elementary charge, times field times x. And so this is a constant, this is the coordinate. So would the slope be higher if I've got a high or a low field? Well, if the field gets higher, so this is F1 and this is F2, then F2 is larger than F1, of course. So the higher the field is, the shorter the distance is at which the energy, there will be an energy gain. So the higher the field is, the higher the probability is to get post-ionization. And so from this, we can even start calculating what the probability is that I get a singly charged ion, doubly charged ion, and so on, just from simple field considerations. But this is also important if we do field ion microscopy. Because in field ion microscopy, the first adsorbed atoms on the tip will also not be able to ionize because they're too close to the surface. They will just be adsorbed, and the electrons in them cannot actually move into the solid because they would need to gain energy for that. Instead, we've got ionization zones. So somewhere out here, at a distance of 1, 2, 3 nanometers, roughly, some nanometers distance, you will have these criteria fulfilled. And so if we look at field ion microscopy, the actual ions that produce the image do not stem straight from the surface, but rather from an ionization zone that's a little bit further out. So what we actually see in field ion microscopy is the field ripples, so essentially the ripples in the field that are created by the surface atoms. Not the surface atom, there's not a direct interaction with the surface atoms. The reason for that is essentially this post-ionization process. So if the atoms are too close, they can get ionized because the HOMO level is below the Fermi level. So essentially here we've got the HOMO level below the Fermi level, and here we've got the HOMO level above the Fermi level. And we can actually calculate that. And this is the so-called Kingham curves. So So the Kingham curves is something you will find in many books. Yeah? And so essentially they're just calculated curves of charge state prevalence versus field. Yeah? So here we've got it for niobium, and I'm just looking for someone that's maybe a little bit more important for us, like nickel. Yeah? So you can see nickel, if we're at 40 volts per nanometer, then we will mostly get, so blue, I guess, would be plus, yeah? Green would be 2 plus, and red would be 3 plus. Yeah? So since we never observe 3 plus, yeah, that's very consistent with what we see here, because in order to start to observe 3 plus, we would need to be at probably something like 45 volts per nanometer, which we're probably not going to get on nickel, unless maybe we can put some nickel atoms into tungsten. And tungsten would have a relatively high evaporation field, and then individual nickel atoms would be exposed to that field, but not typically. Yeah, typically, mostly we would be somewhere in this area, probably somewhere closer to here if we have laser pulsing, because then the energy we put in is more thermal and less field. And if we have voltage pulsing, then the field will be a little bit higher, and we'll get mostly nickel plus. We'll get mostly nickel plus. And I just, mostly nickel 2 plus. And this is exactly what we observe in experiment. If you do laser measurements on your specimens, on nickel specimens, then probably you will see mostly nickel plus. And if you do voltage measurements, you will pretty much only see nickel 2 plus. But of course, you can change the temperature. They can change the temperature also on voltage pulsing, and then you will see the appearance slowly, if you go up with temperature, the appearance of nickel plus as well. And so we can use the charge state ratio or CSR to try and determine what the field is at our specimen. And we can even look at it locally. So maybe on your specimen you might have one phase here and another phase there, but both of them contain nickel. Then you can analyze which charge states you observe in phase A and which charge states you observe maybe. Let's draw a tip like this. And something very common here is you might have a gamma prime here, and you might have gamma here, and both of them contain nickel. But you might observe a different charge state ratio here than here. And then you can go and estimate what the local field is. So you can go and estimate what the local field is. Why could that be interesting for us? Any idea? How do we usually calculate the field? Remember, field equals, in the simplemost approach, voltage divided by some fudging factor times the radius. And so from the charge state ratio, we can go back and calculate what the field is. We know what the voltage is from the experiment. So what could we calculate? Yes, so we could calculate. We could, for example, go and get an estimate for the local radius, which of course we'll get later into things like local magnification, which is a good way to start and estimate what local magnification you might get somewhere. But also we can also look into at which temperature we get which charge state ratio, because then the field is obvious. The evaporation field is also temperature dependent. So we can also use it for temperature calibration. So we can either look at what the local radius would be, or we could look at what the temperature would be. And this is very important, for example, if we do laser atom probe tomography. We'll look in that later on, because if we shoot a laser onto a tip, the absorption very strongly depends on the tip shape. It depends on the tip shape in two ways. First of all, the absorption itself depends on the tip shape, and then also the conduction of the heat away from the tip also depends on the tip shape. Yeah? So if we go into a machine and we set certain measurement conditions, especially for laser measurement, then that doesn't mean very much, yeah? Because we don't take into account what the shape of the tip is. But by using the charge state ratios, we can get back in and locally estimate what the fields are. And honestly, we actually would need to adjust our laser power to match charge state ratios, rather than just going and saying, okay, I put a certain laser power in and then I get the same result. That's actually not what happens. Okay, and this was for perfect metallic conductors, but the reality is we have a lot of semiconductors and insulators, and this is obviously something that interests us very much, because maybe you're interested in some solar cells or into some geology specimens or some biomineralized specimens. And then you have the problem that all of this, everything that we've said so far, hinged on our specimens being fully conductive. Yeah? So essentially, we had no field inside the tip. So the field just started at the tip, and this is also what this sketch says here. Here the field starts, and there's no field inside. Because only then we can say that the local field is essentially directly proportional to the specimen voltage. But in semiconductors and in insulators, what we have is we have field inside, because the so-called Debye length. So the Debye length and that should be lowercase. The Debye length is some length. So the Debye length is the length in a solid within which a charge is being shielded. And the definition of a metal being a metal is that the Debye length is smaller than the atomic spacing. What that means is that any charge is immediately shielded, because you've got a lot of mobile electrons, and that's the definition of a metal, actually, the physical definition of a metal. If we have a semiconductor and insulator, that's no longer the case. So our Debye length is larger than the atomic spacing. And typically it might be some nanometers up to some tens of nanometers. It will depend on how conductive your material is, what the shielding distances are. And what that means is that electrical fields are not immediately shielded. Instead, what you have is you have an internal field. So you have an internal field, and here what we have is a drawing for an insulator where the Fermi level is somewhere between the valence band. So this is the energy of the valence band, and this is the energy of the conduction band. Or if we look into it molecularly, then this is, of course, the highest occupied molecular orbital. And this is the lowest unoccupied molecular orbital, LUMO. Or conduction band and valence band if we're in a full solid. And typically, of course, insulator, Fermi level somewhere in the middle. And what we now do is essentially we bend the Fermi level because we are moving a field in. And through the field, we are bending what the energy of the Fermi level is. Because remember, the energy contribution is elementary charge times field times some distance, very simply. And this is the contribution we see here, overlaid with the charge density that's in here. And what that means is typically that I need a different color. Is that typically what we get is a bending of the valence band, and typically this will happen above the Fermi level. So what we can say here is that here we've got the Fermi level in the valence band, which of course now then becomes the conduction band, whereas here we've got it below. So here we've got metallic states, and here we've got insulating states. Yeah, so here we've got insulating states. What that means is that at high fields, everything is a metal. There is nothing is an insulator, everything is a metal, because on the surface we've got metallic states. Of course, if you look at a specimen, these very high fields are only present at the very tip, and as soon as you go down the shank, the field is going to get much smaller. So most likely we only have this metallic state somewhere up here. So this is one aspect. And the other aspect is we have got a field inside. So if you're some kind of ion inside of here, then you will see a net force. And a good example is years and years ago, our good colleagues in Münster at the time, or was it already Stuttgart, did experiments on lithium in glass. And what they found is that they always got the same kind of distribution throughout the measurement. The reason for that was not that that's the distribution in the specimen, but that they got diffusion in the specimen. So because the ions started diffusing following the internal fields. Okay. And okay, so this was everything on the single atom basis. And now the important thing for us is, of course, we have a very high field. And what we observe is very often our specimens break. So very often if we do experiments, then they end with our specimens breaking. And the question is, of course, why that is. And the reason is relatively simple. If you have a pressure difference, if you have a liquid and a vacuum, and the reason why it's liquid is just because the derivation is there, is that we have a pressure difference if you take a round droplet, a pressure difference that is given, well, by the radius of the droplet and the field squared. And you can actually simulate the stress very easily as distance from the apex. So you can see if we're here at the transition point from here on. So if you have, so this is essentially just specimens with a sphere on cone geometry, and then some cone angle alpha, or whatever you want to call it, which is that angle here. And what you can see is that close to the tip, so up to about some tens of nanometers, it doesn't actually matter what shank angle we have, the stress is always relatively the same. But what you can also see is that the stresses can get very high. As this is stress in megapascals, and you can see here that unfortunately I didn't note down at which voltage or which field this is, but you can see that the stresses are on the order of 10 to the 3 or so, so relatively high stresses. And most specimens don't have strength in the 1,000 or a couple of thousand megapascal range. Why do you think atom probe still works? Because according to this, all of our specimens should break straight away. Well, because they're nano objects. And so nano objects, we're getting closer to the theoretical strength, just like if you have a nanowire. And if this wasn't the case, then we would have the problem that all of our specimens would break. Of course, what we then don't know is that if we have any dislocations in there, for example, would the dislocations just as soon as I put out the field, would they all just get pulled out? Effects like that are not necessarily known and they're a little bit hard to know. Maybe we will in the near future, because our good friends at Jülich right now are building a combined TEM and atom probe, where they could do in situ experiments, and then we might get some insight on what crystal defects do at this temperature if we start cranking up the field. Okay, and so this was all for. This was all for homogeneous specimens. But in inhomogeneous specimens, what you get is local magnification. Because remember, we were talking about ionization energies and how they influence the fields that we need. And of course, if you've got different phases, then typically the atoms will have different bonding energies. Even that might even be very local. You might have a cluster in an aluminium alloy, and then a cluster has a different bonding energy. Because the reason why they form in the first place is because of an energy gain to form, which means stronger bonding energies locally. And here, this is actually an example where we have some precipitates, and I believe this would be aluminium and probably some magnesium silicon precipitates in there, and some clusters. And what the effect is, just imagine you've got a specimen and the field is a little bit higher, or the field necessary is a little bit higher for a precipitate, then of course it will need a stronger radius. Always remember, field is voltage divided by something, divided by typically this fudging factor and the radius. So if the field goes up at a constant voltage, what we need is just a higher radius. And so in this case, what would happen is, of course, that the trajectories in this case would be compressed locally. They would be compressed outwards a little bit. And this area would be magnified. This is what we see here. This is what we see down here. And of course, if you have got some particle or some phase that has a lower evaporation field, then the opposite would be happening and you will get a demagnification. Now, this doesn't happen all that often with precipitates, but just think of something like a vacancy cluster, or maybe you have a helium bubble or something like that. A lot of people that do atom probe do it for nuclear applications, and their helium bubbles are a regular occurrence. And then you might just have a little hole for that reason, and then you get a demagnification and a smaller size. So it's local magnification, but also demagnification. Demagnification. And this changes the apparent size of objects in our atom probe reconstruction. And here we've got a bunch of different sizes from small angle scattering. So from small angle scattering, I don't know if it's neutron small angle scattering or if it's X-ray small angle scattering, but it doesn't matter. It's just a measurement with very good statistics, should very well verified. And if we compare it with atom probe tomography, then we can see that we get a deviation that we here. This is essentially the line where it's the same, and the smaller the object becomes, the more we get a deviation here. Of course, this is very specific that the size in atom probe is a little bit larger observed than in small angle scattering. But depending on what objects it is that we're looking at, it could also go the other way around. But what that just means is the smaller the object is, the more severe that the whole thing becomes. Because the more radius difference I will need to accommodate the local increase in field that I need. And of course, eventually the precipitate is going to be so large that it's the entire tip, and then there is no difference anymore to be had. And so this was just the local magnification. And the local magnification still has no influence on which atom goes where. So all of the atoms up to here all took the same trajectory, because if you have an ion that starts at an energy of 0, which we assume for an ion to have when it leaves, so it starts with a kinetic energy of 0, might have some thermal energy, but that's not a lot. So the trajectories are independent of what type of atoms it is. It doesn't matter what atom it is, they all follow the same trajectory, which is just given by the field. But for certain species, we observe that this is not exactly the case. And this is a paper by Emmanuel Marquis and François Vaupillot. It's already a couple of years old now. And what they were looking at was aluminium and silver. So silver precipitates in aluminium. And what they observe is that there is a shift in the observed location. I should just imagine you've got a large tip. Got a large tip. And then you've got your silver precipitate somewhere here. And what should happen is that you observe in your reconstruction or in your image on a detector, you should observe the absence of the silver atoms exactly where, the absence of the aluminium exactly where the silver atoms are, because that's how solids work. Either you have one type of atoms or the other type of atoms. But in reality, if you look at it, then you can see that the aluminium atoms and the silver atoms are observed in slightly different locations, so that if you start summing the atom counts up, the overall density shows goes down here, and then goes up here. That's obviously unphysical. In reality, we have a relatively constant atomic density. I'm not quite sure what the density of silver is compared to aluminium, but it's not like a factor of something and lower at some point and higher at some other point. And this typically is observed, or it's most prominent at relatively small precipitates, so there is no scale by here, but you can see here this would be roughly around 10 nanometers, there or thereabouts. So relatively small precipitates, but not super small precipitates, but a typical size order that we look at. And this is still, in XY. This is still in XY, meaning the curvature of the tip. But we also get some deviations in Z, and this is what's called preferential retention, which is unfortunately something that I've discovered during my PhD thesis. So typically, when historically we were measuring a lot of precipitation in atom probe tomography, and what happens in precipitation is essentially that atoms cluster together because they have stronger bonding. And the stronger bonding also means they become less mobile. But I started looking at a lot of grain boundaries, and in grain boundaries, the energy gain is more structural. An atom goes somewhere because there is a larger gap. But it might not necessarily have a lot more bonding locally. It just might have a lot more space. And it might be a little bit harder to ionize than the surface atoms. And here we've got 3 examples. So this is boron in nickel, this is carbon in nickel, and this is copper in aluminium. And boron and carbon are obviously atoms with relatively strong electronic bonding, so relatively hard to ionize. Copper is a little bit easier to ionize. And so essentially, if we look at the distribution, if you would measure a tip, if you would look at a distribution across a grain boundary, so these are all grain boundaries, and what you would expect is some kind of segregation profile that looks symmetric. Yeah? We to date don't necessarily know exactly what it should look like. Should it be some Gaussian distribution? Should it be a delta function of atoms just sitting in the grain boundary plane? We don't necessarily know. Yeah? All we can do is do some DFT simulations to get an idea. Yeah? But then it becomes a little bit difficult to also assess the effect of strains you might have locally. So we don't necessarily know what it should be, but what we can be fairly certain is that it's probably going to be symmetric, and even if it's asymmetric, we should observe the longer tail up or down in about the same at about the same frequency. So half of the specimens should probably have the segregation pointing upwards and half downwards. This is not what we observe. What we observe is always that we get a little bit of a broader segregation profile downwards. And this is essentially the profiles that we measure. So you can see here the 0 point is always somewhere here, and we always have a little bit of a tail. And what that means is that the atoms have some stickiness to them, and it takes them a couple of atomic layers before they come off. It takes them a couple of atomic layers before they come off. And that essentially means that the probability to come off is roughly constant. This is an assumption. We don't necessarily know. And if the probability for something to come off of a surface is constant, then of course the probability in each layer is some constant factor compared to the layer before, which means we have an exponential decay. And we can then go and derive a decay constant. If decay is very prominent, we can go and derive a decay constant for each element at a certain measurement condition in a certain host material. And we could then also go and use a deconvolution, for example, to get rid of that artifact, but then obviously you need to know a lot about how that actually works and if it's constant. And I don't think anybody has put enough effort into any kind of system to be able to do that confidently. But I, for example, have done it for copper and aluminium and other things in aluminium, where you then see a distribution that's much closer to what you would expect compared to what you observe. Because, for example, if you quench aluminium, you all know you have a precipitation-free zone, so you have some segregation just goes straight into the atoms that segregate need to come from somewhere. So you should have a few more atoms around than you have in the middle. And if that's not observed, then it's probably a problem with the measurement. Or if it's only observed on one side, it's probably a problem with the measurement. And that's exactly what that is here. So here I've tried to bring some sense into the whole thing. So we have this retention coefficient, which is essentially the ratio of probability of atoms to come off within a nanometer compared to the field of the solid, taking the field of the solid compared to the field of the matrix. So if you have a solid with a very high field, like carbon, in a matrix with a very low field, like aluminium, for example, you would expect it to be a lot of retention. And the other way around, if they have very similar fields, there would be very little retention. But you can see it's all over the place, so there's not really any systematic to it. So sometimes it happens, sometimes it doesn't. And I think we're probably going to need some quantum mechanics to try and understand that. But here, this is the example that I've mentioned. This is copper in aluminium, and this is the observed distribution. And if I derive a retention coefficient and do a deconvolution, then I get, does everyone know what a deconvolution is? Yes, no? Okay, so a convolution is, just imagine if you look at a blurry picture. Typically, the blurriness comes from some kind of Gaussian function, or because you're going through some kind of aperture. And then the Gaussian distribution or whatever function you have that smears everything out, that's a convolution function. And a deconvolution is the inverse operation. So you're trying to take sort of some smearing out of a function. What it always means is that you amplify noise, because if you smooth things, then any noise would disappear. But if you have measured noise on your measurement, then you don't know what the noise part is and what the real part is, and so we'll get a lot of measurement noise. But if you do that here with the deconvolution, you get a distribution like this. And this is pretty much what you would expect from a segregation profile. So essentially the copper atoms that were sitting within 5 to 10 nanometers segregated into the grain boundary, and that's what makes for the grain boundary segregation. What does it mean practically for us in atom probe tomography? It just means that if we look at concentrations at an interface, you can see here, this is the measured concentration, and this is the concentration that's probably much closer to the real value. What it just means is that concentrations at interfaces don't have a direct meaning. They don't make any direct sense. But what we could do is we could count the number of atoms that are in this hump, and that should be relatively constant. This is what we call the interfacial access. So if you see atom probe data and someone says this is a concentration at the grain boundary or this is the concentration at the interface, then that's probably a pretty meaningless number, because the way that these artifacts happen would obviously also depend on whether the grain boundary is upright, because then you wouldn't have that, or if it's entirely perpendicular to the axis of measurement, because then this effect would be relatively strong. As it depends on the orientation, it depends on what the matrix is and what the solid is. So at interfaces, the concentrations don't have a direct meaning, but rather count the atoms that are there, and this is then a lot more independent from things like orientation. Okay, so this was a very quick overview of the most important bits about field evaporation physics. And the last thing we're going to look in today is the pulsing. So how do we get a reference time? This is essentially ties into the field evaporation physics, because typically we had field effects and we had thermal effects. And of course, once we get into laser pulsing, we also have thermal effects. And essentially, we have two ways of doing that. One is changing the voltage, changing the field, and one is changing the temperature. So typically, our experiment starts at some standing voltage. So we have our specimen at the voltage where nothing happens. And the reason why we do that is twofold. The first reason is technical. So it is relatively hard to produce very large pulses. So just imagine we would now measure our specimen at 10 kilovolts, and you would have no field without the pulse. That would mean we would have to produce a 10 kilovolt pulse, which is doable, absolutely doable, but it's a pretty brutal pulse. That's one effect. That's one part. And the second part is, actually three, I should say, because specimens also don't like very harsh pulses as well. But you could say, I've got a specimen that survives everything, then maybe that would work. But the other part is also that contaminant gases adsorb on the surface of your specimen, and then they would just come off during your pulse, and you wouldn't just get the atoms that you're after, but also any contaminant gases coming off during the pulse. And so essentially, our standing voltage is both there for technical reasons and also to keep your specimen clean. Of course, if you've got an ultra clean atom probe, then maybe that's not as necessary. We haven't tried it on our titanium atom probe. Maybe it's not as necessary. But this is typically the case. But you can also make use of that. So some people do chemical atom probe. So if you look at your atom probe tip, and your atom probe tip is actually, the end looks kind of like a nanoparticle. And nanoparticles are very common catalysts. And so what you can do is you can do catalysis experiments on an atom probe tip. So you put a little bit of gas in, the gas absorbs on your tip, it does some reaction, and then you put in a pulse and pulse off the gas, and then you can know from the flight time what gas it is. And that's the so-called chemical atom probe. There was a lot of research on it in the 70s and 80s. Then it died down a little bit. Only one group mostly, or one or two groups carried that on. And now there's a little bit of a renaissance because with progress of engineering, you could do that a little bit better, but people need to get interested a bit more. But we have colleagues, for example, at PNNL in the US that are doing things like that are building also chemical atom probe right now. And obviously you can follow that with interest because you could then vary the time between the pulses, as the pulse of the reaction products at different times, so you can dynamically follow the progress of a reaction. But typically, that's not what we do, and if any gases come off, then we don't want them. What is the most important gas that comes off? Hydrogen. Because hydrogen, we have a residual in the vacuum system, in any vacuum system apart from the titanium atom probe, there we don't have any. But in any other systems we do. Okay, and it's relatively hard to ionize, so unfortunately it doesn't come off before the pulse. It only comes off with the pulse. Okay, and so we've got our two ways. So remember, if we go back to our very first model here, so we've got a barrier to overcome, and that barrier can be overcome thermally, or we can reduce the field enough that we can overcome it by field and just have essentially what we're adjusting is the amount of thermal input versus the amount of field input. And so what we can have is voltage pulses, and what we can have is laser pulses to heat the specimen up. That is what we do right now. Of course, the reason why we use laser pulses is not because we heat. This is an unfortunate side effect, that it works by heating. But what we actually want is ionization. And it just happens to work by heating because that's what our current lasers are able to do. But ideally, what we would want to do is we would like to increase the field by laser, or to input the energy as ionization energy, as direct ionization energy. And there are efforts. So this is conventional laser. This is voltage pulse. And the question is then, can you have a laser that either increases the field or just directly ionizes? And currently our colleagues in the US at Ian Caramonti's lab, for example, they're using very short wavelength lasers. So lasers with, I think, 20, 30 nanometer wavelength to do direct ionization experiments. Or our colleagues in France have used terahertz pulses where the field is locally enhanced. What we do here in Erlangen is we use ultra-short wavelength, ultra-short pulses in Peter Hommelhoff's lab. And of course, what that would do is it would keep the temperature constant, because the one downside that we have with the laser is we increase the temperature, so all kinds of things happen. Most importantly, the fields go down. So we get molecular ion formation, we get low charge states, we get a lot of different charge states, and we get surface diffusion. So if we can do voltage pulsing, we do voltage pulsing just because the data is more interpretable and it's just higher quality. But for a lot of specimens, that just won't work. And so if we have voltage pulsed atom probe, essentially what we have is a pulse with a typical width of about 1 to 5 nanoseconds. It depends on what kind of pulsar you have. So the one that we use in our home built instrument has about 1.5 nanosecond full width half maximum, and it's a very, very, very good pulsar. But I, for example, have some older pulsars that people just donated to us, where the pulse width would be closer to 5 nanoseconds or something. Why is that important? The reason why it's important is that we have if this is our pulse, this is the pulse that we have here, over time. Oh, sorry, that was not what I was about. So if this is the pulse that we have, the white thing is the pulse, then of course the field evaporation probability is exponentially dependent on the ratio of field at the current time to the evaporation field. So a very high evaporation probability, which is the solid line here, only happens in a very, very short, in a very narrow part of the pulse itself, sub nanoseconds. So if you look at this here, then maybe here in this area, this is where we might get the field evaporation. But what that means is that we do still have some energy variation in here. So one ion might come off here, one ion might come off here, and then it will fly. So if we just draw where the ions go, then the ion might be here at, say, here at 0 nanoseconds, then here it might be at 1 nanosecond, here it might be at 3 nanoseconds, and so on. Of course, it accelerates with a constant, in the field it will accelerate constantly, so the speed will go up linearly as a rough approximation. So the question is, then how long is the field there? Because if your atom comes off earlier, then it will have a little bit more energy because the pulse will eventually end and the field will be switched off at the specimen because electrons move much faster than ions, so I can switch off the field and then no driving force is there anymore, only the DC field. And the question is, if the atom comes off earlier during the pulse, then the field will be on for longer than if it comes off later during the pulse. And the result of that is that we get an energy distribution that we observe as, if we plot the frequency versus the flight time, and as a result from the flight time also of the mass to charge, then we get a maximum, but we still get some ions that are lagging. In energy, and that need a longer flight time, therefore. And this is why we get a finite mass resolution, because the atoms don't come off at the same time, and so they see different amounts of field, different amounts of driving force as they move away from the specimen tip. And this is also why we talked about things like reflectrons, because if you have a reflectron, then the ions that have a little bit more energy, we can make them fly deeper into the reflectron so that they take a little bit longer, and then we can even that problem out a little bit. But in general, depending on where exactly, or when, sorry, not when, but not where, but when during the pulse the ions come off, they will have slightly different energies. This is the limit of mass resolution for a voltage pulsed atom probe. If we have laser pulsed atom probe, then the ions will all have the same energy, but they might come off at different times, because we've got cooling of the tip. But let's look into the basics. So if we've got laser pulsed atom probe, then we have femto or picosecond lasers. So the first lasers used were femtosecond lasers, but then people tried out if it makes a lot of difference if they're femtosecond or picosecond, because good Lord, I have no umbrella on me. Anyway, people have tried whether femtosecond or picosecond lasers make a difference, and it doesn't seem to make a difference up to lower picosecond levels, because the heating and cooling times are in the nanosecond range anyway, so it doesn't make much of a difference. We have found if you go to very low femtosecond and attosecond, then it starts to make a difference, but not in the range that you can typically buy lasers in. So the laser that we have in our commercial atom probe, it's around 10 picoseconds in the LEAP. That's our commercial atom probe that we have. And in the laser that we get on Monday, that has around 300 femtoseconds. And I don't expect there to be any noticeable difference from the different pulse durations. Because all that happens is that the laser beam gets absorbed, and what we get is temperature versus time. Laser pulse hits, temperature goes up, and then eventually we'll have some heat conduction away from the tip. Of course, then this depends, so this, let's call it TC, cooling time. So the cooling time will depend on, first of all, how thermally conductive your material is, of course. If you've got a good thermal conductor, it's going to go very fast. Bad thermal conductor, it's going to be longer. And it will depend on how, where and how your energy is absorbed. So if you have the energy absorbed closer to the tip, then probably you need less energy that's then quicker to remove. And if you have a smaller spot, then the same thing would be true as well. So the closer we can input the energy, the less to the tip apex, the less energy we need, and the quicker everything will go. But this here, this is some of the earliest experiments. That's actually Baptiste Gaud's PhD thesis, where they borrowed a laser or two lasers from a company, put them onto the atom probe, shot them at tips, and got really, really good results. This is why I have high hopes that if we get the laser next week, it's not going to take us 3 years to laser atom probe, but rather we'll put the laser down and we'll do our measurements. And this is tungsten, and you can see what you would expect. You can nicely see the individual atomic terraces. And this is the mass spectrum, so very, very good mass spectrum as well. But the main difference being that here, the probability for the atoms to come off over time will be somewhat proportional, will have some proportionality to the temperature. And what that means is that the uncertainty in evaporation time will be proportional to this cooling time here. So the faster we cool, the better the mass resolution will get. Why is that important? Because if I have voltage pulsing and I make the flight path longer, then the energy difference wouldn't change at all. So still one atom flies faster than the other. So I can make the flight path as long as I want, and I wouldn't get any better separation between the atoms. Here, that's not the case, because the separation here is essentially delta T or delta flight time between ions of the same kind, let's say tungsten 3 plus 180, to the flight time. And of course, the flight time we can increase. And if the cooling time stays constant, that means that my mass resolution will get better the longer the flight path is. So it's exact same cooling conditions, longer flight path means better mass resolution. And in the 80s, there were first experiments with nanosecond lasers, Tien Song, for example, and Gary Kellogg. And Tien Song built a laser atom probe, a one-dimensional laser atom probe with an 8-meter flight path or something like that. They made a hole into the lab wall and made a drift tube that's like 8 meters long, and the detector very far away. Obviously, they only collected very few atoms, but then you're extremely well equipped to distinguish isotopes and different elements and so on. because, for example, you can think of nitrogen-14 and silicon-28. It's very similar in mass, so silicon-28 2+ and nitrogen-14+, very, very similar in mass, and then you can even distinguish them because your mass resolution becomes good enough. For us, usually we are limited these days because we want to have a good collection angle. So the further you move your detector away, the fewer atoms you're going to see. So it's kind of a trade-off. You can buy a bigger detector, put it a little bit further away. But the good thing is, it's a very straightforward way to increase the mass resolution. Okay, so we can actually set up a relatively simple thermal model for that, and that's already happened a long time ago. Essentially, you can just simulate what would happen if you deposit energy at the tip, and then you have nonlinear thermal conduction, because remember, we're at relatively low temperatures, so you can't just assume that your thermal conductivity is going to be independent of temperature. It will be strongly dependent on temperature, and then you can just simulate that and try to understand what the tip temperature is, and I believe that was for tungsten. And then you see, okay, we're moving close to room temperature for the tip apex temperature. And of course, that means that we can go even higher in temperature, that we will see mobility of atoms on the tip. So the higher you get in temperature, the more mobility, the more diffusion of atoms on the tip you will see. And remember, atoms actually move in gradients, in field gradients. And if you remember what atom probe tips looked like, I always drew them as sort of like a sphere on cone, but in reality, they might have flatter parts, and it might be a little bit faceted because of crystallography or because of different phases and whatnot. And what it means is we have field gradients, and we have mobile atoms because they have thermal energy, means that they can move laterally. This is sort of the downfall of laser atom probe, that we heat the specimen, and as a result, we get enhanced mobility and we get atoms moving on the surface. And this is just an estimate of peak temperature versus energy flux for platinum, tungsten, rhodium, and tungsten with a 5 nanosecond pulse in this case. So this would be an atom probe from the 1980s. Compared to an atom probe from now. You can see that the peak temperatures are much higher. So back at that point, you could do a good analysis of mass spectra, but the lateral distribution wouldn't have made much sense because your atom probably would have diffused around a lot. And so depending on what the thermal conductivity of a material is and the absorbance is, you might get different peak temperatures, and they can be in the range of a couple of hundred Kelvin. That's why I said they might very well be above room temperature, depending on how much diffusion you would get at that temperature, and that's not really optimal. So the question is now, what influences that? And essentially, just imagine we've got a tip. What you want to do is you just want to heat the very apex of the tip. And the most trivial way to do that is to have a very small spot. If you have a very small spot, then obviously just heat the apex, but that comes with its own challenges because it means you need to focus a laser point very closely to a tip. You might need some optics that are very stable and so on and so forth. So that's challenging but doable. And the other influence that we have is laser wavelength. So laser wavelength, and the reason for that is that this is actually something that came out of the Rouen lab already now close to 15 years ago. So this is when they published it. And essentially, what we have is that we have a laser beam that's absorbed by a sub-wavelength object. So typically, if we look at shooting laser beams at something, then most of the objects we shoot them at are larger than the laser beam. It's larger than the laser wavelength. But here, the atom probe tip typically is smaller than the laser wavelength, or at the same order of magnitude. So the absorption is not just a uniform absorption, but it depends on the geometry. and we'll have some maxima and some minima. Do I have some animation there? No. We have some maxima and some minima. So if I look at the absorption intensity versus x, then it will have a maximum here, and then another maximum here, and this is where tip apex is. So this is where everything's happening. So you're heating here, but the tip apex is here. So your thermal energy is deposited here. It needs to move to the front and then get absorbed again. And of course, that's a process that takes much longer than if we heat close to the surface. So here, this would be for a 1200 nanometer laser. But if we instead take a very short wavelength laser, and I unfortunately don't remember which one that was, but I guess that was the 320 nanometer laser, then the intensity versus distance will look something like this. And so our first maximum of heating will first of all be much higher compared to the other ones, and also it will be much closer to the apex of the tip. And as a result, we need to input a lot less energy for the same amount of temperature rise, and that energy will then be transported away much quicker. And of course, ideally, you have the combination of both. You have a short wavelength and you have a small spot. But all of the results that I've shown you here, this is all done with a relatively large spot. I think 100 microns or something like that, something that you can visibly see. Don't look into the laser, though. Don't say, I said, I want to see how large the spot is. It's not good for your eyes. And this is the reason why we're moving to smaller and smaller wavelengths. Typically, what we have in laser sources, most laser sources are infrared laser sources. If you're a titanium sapphire laser, for example, or a fiber laser, very often they're in the infrared range. So what we have are so-called harmonics generation, second harmonic generation, third harmonic generation, fourth harmonic generation. So we double the wavelength, triple the wavelength, quadruple the wavelengths. And these systems that can do that have gotten better over the years. And so with each generation of atom probe, we usually had the ability to access lower and lower wavelengths. So the first generation laser atom probes typically worked with green laser, because there was a second harmonic. Then the atom probes that we have in our lab downstairs that were now the standard for more than 10 years, they all worked with the third harmonic, which is about 350 nanometers. And now we're seeing lasers good enough to work with the fourth harmonic. And the one that we get also goes up to the fourth harmonic. And if you buy a brand new atom probe, you also have a fourth harmonic. And hopefully the absorption is closer to the tip. This, of course, really all just is on the basis of these very few papers. And some people that do laser physics have very different opinions and say, okay, maybe you oversimplified your problem here. So on our laser, we will have the ability to choose between the fundamental, which is infrared, the second harmonic, which is green, and the fourth harmonic, which is 260 nanometers roughly. We don't have the third one because you only get 3 ports in this case. And so we can try out if it really is just this wisdom here, or if there's a little bit more to the story. Because of course, different materials also absorb differently, and these simulations are for metals, for ideal metals. And what we can get is essentially this. We start from a base field, and we go and produce a thermal pulse. And the energy of the thermal pulse needs to be high enough that for all different atoms that we have, the ionization goes above the threshold. This, by the way, also true for the field pulsing. Here we need to have a pulse high enough so that our atoms A and atoms B, if we've got a tip with A and B, that both of them get ionized, and the same for the thermal pulsing as well. Otherwise, we can have so-called DC field evaporation, so that some of the elements might come off in between the pulses, and we will not measure them. Okay, so this is also, we're over time, so I'll make it quick. This is essentially what that looks like. So here you can see this is the older generation of atom probes that I started out on, the 10 micron spot and the 500 nanometer laser. And you can see you get these long tails because longer cooling times. And these are the new ones that have a 3 micron spot and a 355 nanometer laser. You get a much, much better mass resolution. So now what will our instrument have? Well, we will have a 257 nanometer laser, and we will have a very small spot in probably the sub-micron range, because we spent a lot of money to get some optics very close to the tip, so we can get very, very small spots. And then we'll see whether that helps at all, or whether that all was, whether there is additional effects that we haven't considered. Okay, and with that, we're at the end of a very quick rundown of field evaporation physics. And then we'll meet again in 2 weeks. And hopefully then we will already have all the parts for our field arm microscope. So we will go downstairs and start building our field arm microscope.